Any questions? So again, like I'm not so familiar with this mean field analysis, but my question is that why LLF is a good candidate as compared to the potentially other alternatives for this analysis, and is this just because the analysis is elegant, or in practice also this LLF is a good idea?
Well, there are many papers that have analyzed different scalars. I mean, when it's difficult to come up with the optimal scaling in some sense. For instance, the one that reneges the least amount of work or something. One thing that is I didn't say in the presentation, but the main difference between these scaling problems on EV charging or charging in general and classical deadline scaling is that partial service is useful. I mean, people can receive 50% of their battery load and they will be somewhat happy in some sense. Whereas in a scaling system for computing, for instance, if you do not finish the job completely by the deadline, then it becomes useless. So you lose your processor time. Okay, so this has been less analyzed. This setting of parallel service, but with partial work, has been less analyzed in the literature, and it's not clear what the optimal policy is. LLF has been identified as having very nice properties, but we are not sure about the optimality of LLF. It certainly is pretty optimal in simulations in terms of the amount of reneging work. So it's one of the policies that provides the most amount of work by the deadline to all users.
Sounds good. And like a quick follow-up question. So right now the objective is just to maximize the energy that is delivered to the charger, to the EVs. Is this true?
This is one of the main objectives. In practice, if you have if you do a mean field analysis, I mean, if you go into the mean field limit where the arrival rate is large and you're in overload, then in practice all efficient policies deliver the same amount of work in the mean field limit. Okay. But efficient means that it does not lose any charging opportunities in some sense. So if there is someone, it's not non-idling in some sense. If you are around the capacity, I mean, more analysis is needed in the zone where if you are in underload, then every policy works well. If you are in overload, then every policy delivers the same amount of energy, the amount C times the time that you spend. And the thing is, near the capacity, some diffusion analysis will be needed to distinguish between policies. And this hasn't been done to my knowledge. There are some recent works on deadline policies using Scottercode maps and measure value processes by Rami Attar and people and other people. I can't recall it right now. So this is an interesting area of research for mathematics. From the applications point of view, I think least laxity first is a very good policy. The only thing, and I think the only thing that precludes you from using it is this deadline uncertainty. So you may not know the deadlines at all. That would be so. If you have to go to a deadline oblivious policy, then you have to stick up with something like FIFO, LIFO, things like that. And it's not clear what's the best you can do there. Okay.
Sounds good. Perfect. Thank you. Okay, so I think we are done right now.
I have also a quick question.
Sorry.
More related maybe from the technology. So I think you are assuming that the charging time of the battery is linear with time, right? So the energy more or less.
Yeah.
Okay.
More or less. Yeah.
Okay. Because my question is the following. What happening with the batteries of the mobile phone is we have a fast charging in the very beginning, and then to complete, it's not linear, so the charge is not linear.
Yeah, but so it has two regions. You have a fast charging, which is by using constant current and then you have some kind of a constant voltage. I mean, I'm not the expert on the electrical side.
Uh-huh.
We have a colleague that does that precisely, but I mean, if you consider that your car is full when you reach 90% of the battery, for instance, which would be a good threshold because you don't want to overcharge it, then you can assume that it's linear up to 90%, for instance. So if you consider full battery 90%, then the model is right. If you want to push the battery more, then some subtleties may appear.
Okay. No, interesting that you already considered the issue and nice. So, thank you. So, okay, I will stop